You have seen before. Okay, we're just starting equations where we have not just one variable but two variables. What is this going to lead us into? What kind of a graph, what kind of a function do we look at when we're talking about two variables usually? The most basic function that we look at. Yeah, on a coordinate. And what's the most basic of all the functions that you learned or that you've seen so far?
Slope.
A what?
Slope.
Oh, yeah, what's it called? It's not a parabola, but a linear or a line. Okay, so we're going to see how this is going to take us into lines in a little bit. But we're going to start with the idea of what is an equation with two variables. Well, it's really just called an open sentence in two variables, meaning there are several possible solutions to these equations. Okay, there are many. And when you plot all those many solutions on the same plane, you connect them and you make a line. That's really what a line is. A line is a visual representation of all the solutions to an open sentence. Okay, so if you had something like 2x plus 3y equals 12, that's a linear function. If you come up with x, y coordinates for each possibility for x and y, those are all of the solutions, which there are infinite of them. Because as you change x, y changes. Okay, assuming that it is a function. Okay. All right, so let's go into this. Let's start. Again, we have a pair of numbers. So we're going to notice that our answer is no longer going to be one individual value, but now it's going to be a coordinate value as a solution. Okay, we're going to look for coordinate values. And we're going to see that when we have open sentences in two variables, there are going to be many coordinates or pairs of numbers that are linked together by that line. Okay, by that line. So example 1 is very simple. Find 5 different solutions to the following open sentence. Now, it doesn't matter what they are, just find 5. So you can literally pick 5 values for x and find out the y's. Or pick 5 values for y's and find out the x's. Traditionally speaking, in math, you assume x is the independent variable. Again, when you're in physics, you'll learn that that's time and distance and stuff. So all we know now is just remember, or the easy way to think about it mathematically, is that x you're going to pick a number for. Y you'll get a number for. But you can do it backwards. It doesn't matter. You can pick values for y and come up with values for x as a result. Okay, so let's say, for example, give me a value for y, Ryan. For x, it doesn't matter which one. 5. All right, so if x is 5, what does y become? How do I figure it out? Exactly. Plug in the 5 for x and solve the resulting equation. So if I plug in a 5 for x, I get 4 times 5 plus the 3y equals 24. So this is going to give me a 20 plus 3y equals 24. I subtract 20 from both sides by the additive property of equality, giving me 24 minus 20 is 4, and thus y would be 4/3. Okay, 4/3 when I divide by 3 on both sides. So I get a y value of 4/3. So again, I can pick values of x and come up with values for y every single time. Now, I may not want to solve this equation over and over and over again and get y every time, right? So what might a better, shorter way to do this be, Luca? Yeah, or just solve for y, let's say, for now. Okay, it doesn't matter what format it's in, really. But as long as it's solved for y, it makes life easier. So algebraically, how do I solve that for y without a number in for x?
Without a number for x, we subtract 4x from both sides. That equals 3y minus 4x. Divide that by 3. That equals y equals 8 plus, plus 3/4x.
Yeah, 4/3. But you can leave it like that too. That's fine. Okay? So we're going to end up getting 8 minus 4/3 x. But again, I would just leave it the way it is. Y equals 24 minus 4x all over 3. So this is my representation for y when solved, which makes more sense if I'm going to pick values for x in this case. Okay? Now, let's say you wanted to just, pick values for y. What could you do instead of solving for y? You're going to pick values for y and plug in numbers like 2, 4, 5, 7, -2 for y and come up with all the x's. I don't want to solve for x 20 times or 5 times. How would I change this? What would I do instead of what I just did a moment ago? What would the difference be? Sabine? Yeah, so solve for x. That's what Sabine is saying. She was going through the explanation. So if you're plugging in values for y, solve for x generically. So instead of solving for y like we did here, but since we're picking values for x, it makes sense to solve for y. So if I pick any values now, so I list, let's say, 4, -2, -1, 0.5. Let's say those are the values for x. Now I can simply just plug those into this equation quickly and come up with a y value every time. Okay, so that's why we usually, in mathematics, solve for y. Other reasons you're going to see this chapter are so they can be in forms that are recognizable, like slope-intercept form, or point-slope form, or standard form sometimes actually useful. It depends on the problem. This is given in standard form. Okay, so if I were to figure out the next 4 values, quickly just plug in a 4, excuse me. So 4 goes in here first. 24 minus 16 gives me 8. 8 over 3 is 8/3. Everything's going to be over 3, obviously, right? We all see those thirds appearing there? Next, -2. 24 minus -8 gives me 32. 32 over 3, 32/3. Okay, it's not going to be divisible by 3 in that case. A -1 will give me a 28 over 3, which is not divisible by 3 either. And finally, 0.5. That'll give me 24 minus, what's 4 times 0.5, quickly? Anybody? 2? So 24 minus 2 is 22 over 3. All right, so those are all the values of y. And now what I've got is 5 possible solutions. How many solutions are there, though? Infinite many. Infinitely many, okay? Now, assuming that it's a function in x and y, there are infinitely many solutions. Is this too simple? Does it make sense so far? Okay, because this is just the beginning of linear functions, so we understand where they're coming from. It's coming from the idea that you have a multitude of solutions here. Now, if I were to be jumping ahead and looking in like the next few sections in this and visualizing this as a student, I would think about this, how it would look on a graph. 5, 4/3. Now, obviously, along the y-axis, we need increments of maybe, let's see, we're up to 32/3. That would give me 10, right? So let's go by 2s. And I'm just visualizing this right now. And along the x-axis, we went up to 5. So we'll go by 1s there. So visually, we can get an idea of what this looks like already. Okay, we could say, all right, 5 4/3, over 5, up 4/3. Well, 4/3 is a little bit more than 1. So if I'm graphing this for now, just for estimating purposes, it's going to be like right here. Okay, because again, right, this is where 2 would be. If I go over, that's maybe 2. So halfway would be around 1 right there. Then I want to go to the next point, 4, 8/3. What's 8/3? What's 8/3?
Almost 3.
Almost 3. 2.6 repeating. Almost 3. Very good. So go to 2, right? And then 3 would be about here. And we're at 4. So it's about here, maybe a little bit lower, like right there. So I put another point right there. That's the second one. And so forth and so on. And what are you going to see as a result? You're going to see a linear function evolve. You're going to see a linear function show up. Up at, at -2, we're up at 10 almost there. Okay, we're, let's see, 10.6. That'd be up here. At -1, we're at a little bit less than 10. So that's going to be over here-ish. At 9 change. And then at 0.5, we're at 22/3, which is around 7. So that's around here. And what you'll notice, obviously, is that there is a linear fit to this. And I'm trying to do my best to go through the data, okay? But you see that linear trend, and it's going down. Now, obviously, as the year progresses, we're going to see that, well, it's because there's a negative slope that this is going down. And there's a certain y-intercept, and so forth and so on. But the solutions that you come up with for open sentences are where graphs really come from. Okay, that's where your data points enable. Okay. If we want to solve the equation, okay, if the domain of x is given, what does that mean? What does the word domain mean? We haven't talked about domain yet. We haven't really gotten into 2 variable functions just yet. Niall, what do you got for domain?
So you shift the x coordinates right to the side of x?
Yeah, the set of values that x can take on. Very good. The set of values of x coordinates. So it means that in this problem, we're specifying the x values to be -2, 1, 5, and 7. So simply put, you're given the x values to start. So this will be the same process as before. Go ahead and do this yourself real quick. just to check that you got this down pat, please. Okay, you're given the X quantities, and you're to come up with the quantities for Y, please. And I recommend, again, that you do what I asked, or that what I recommended before, which is solve for Y. It'll just make life easier on you. What do you got for negative 2? What do you get? What do you get for negative 2 as a Y value? Go ahead, Mike. Negative 2/3, very good. For positive 1, what do you get, Luca?
2 1/3.
2 1/3, good. 2 1/3, which in improper fraction form would be 7/3. 7/3 for those in improper. For the number 5, okay? 19/3, okay, or 6 1/3 if you converted, 6 1/3 or 19/3. And the last one, go ahead, Kel.
25/3.
25/3 or 8 1/3, okay, or 8 1/3. So those are the 4 values that you should get as answers for this part. Can we move on? Is that easy enough, right? All right, let's take a look at this last condition, or this second to last rather. We got one more question where we're told that Paul is $22. Okay, Paul, I happen to use your name. And he buys notebooks costing $2 each and binders costing $5 each. If he spends all $22, how many of each does he buy? Now, you might know like right away how much or how many of each, but you have to think about the fact that for this kind of a question, there might be more than one answer, right? Give me one possible answer off the top of your head. Off the top of your head that he could have bought. Go ahead.
4 binders and a notebook.
4 binders and a notebook. I absolutely agree. 4 binders at $5 each is $20. A notebook for $2 gives us $22. Absolutely. So 4 binders and a notebook. What else? What's another option of answer?
6 notebooks and 2 binders.
6 notebooks, giving us $12, and 2 binders, making another $10 for $22. Very good. 6 notebooks and 2 binders. There's one more possibility you wouldn't actually think of. Paul?
11 notebooks.
Yeah, 11 notebooks. Just having no binders. 11 notebooks at $2 each gives you $22. Now, visually, how would you think about this? This is what you would think, right? He's got $22, and it's $2 for a binder. So what do I start with?
2
Good. $5, sorry, $2 for a notebook, $5 for a binder
5 plus 5y
equals.
equals 22.
All right. Now, can you have fractions of a binder? Can you have a half a binder? No, you can't have a half a notebook. I mean, you could technically, you could half of it left, but you can't buy at the store half of a notebook. So what it means really is that our domain and range are limited to what types of numbers? Our domain, x values, and range are limited to what kind of numbers?
Integers.
Yes, specifically, you can't have negatives, so you can even be more specific than integers. What's the subset of integers that are only the positive ones?
Real numbers.
That's the average set, real numbers.
Whole numbers.
What is it?
Whole numbers.
Whole numbers. Whole numbers. It does not say counting numbers because counting numbers start at 1. Whole numbers start at 0. And we saw a moment ago that you could have 0, what is the second one? Binders and 11 notebooks. All right, so clearly again we said you could have 11 notebooks and 0 binders, and that is true. What was the other option? You could have 4 binders and 1 notebook. And then you could have 6 notebooks and what was the other? 2 binders? Now, I'm only listing those right there. But what you would have noticed is this. If you tried values for x and y, all the other ones would give you what kind of numbers? Like pick a value for x that's not listed here, Will. Give me another value between there somewhere that's not listed. 8. Okay, if 8 is x, that gives me 16 plus 5y equals 22, which tells me 5y equals 6, and we have 6/5 of a binder. And clearly we cannot have that, right? This would be 1.2. So that answer choice doesn't make sense because you can't have 1.2 binders. So the simple way to do this, obviously, for a problem like this, is to make a table of values. And look at the table of values and see which of them are non-negative and whole numbers, actually. Non-negative integers. Okay? Non-negative integers, as Ryan told us, whole numbers. Okay? And again, there are only 3 possibilities that work. If you try any possible value for x beyond this, anything from 0 to 11 outside of this will give you decimals. Anything greater than 11 for x will give you a negative value for y, which doesn't make any sense. You can't have a negative amount of binders. You'd be like going to the store and getting more notebooks than you could and trading them in your old binders. You know what I mean? Like negative in a sense. Okay, so if you got -1 as the answer for binders, I mean, you'd have to sell that binder for $5 to get more notebooks, which is not what they're doing here. It's not bartering, you're just buying. All right, so those are only 3 possibilities. But again, how would you figure this out? You would try values for x and y, or try values for x, come up with the y values, see which of them are not decimals. These are the only 3 that are not decimals. If you pick up on a trend, the minute you try anything bigger than 11, you get negatives here, and then you can stop. You never want negatives for number of binders or objects. Okay? All right, let's go to the last one first. This one's a little bit tricky. All right? So I want to give you a minute to think about it first, and then we'll go over it. But let's read it together. Find all positive 2-digit odd numbers with the following property. When the digits are interchanged, the result exceeds the original number by more than 36. By more than 36. The result exceeds the original by more than 36. So give me an example of a 2-digit number. It does not matter what number. Give me any number that's 2 digits. 45. All right. 45. Flip the numbers around. What do you get? 54. Is their difference more than 36? It's not. Do you want to do this 95 or 49 times over and over again? You don't, right? So we use algebra to make things simpler on us, just like, remember the distant rate problems? Anybody could sit there and try rates and try rates and try rates to figure out what the distance traveled was, but you write a formula for it, it makes it a lot easier on you. So try and come up with a way to represent this. Okay, this is not an easy problem. Okay, it's not an easy problem at all, but try and think of a way to represent this. It might not come to you, that's fine. Okay, but I just want you to think for a little while and try to come up with an idea of what you might do. Just jot it down for now. I'll come look if you'd like to see if you're on the right track, if you have an idea. So you're on the right track. Can't use that. You're on the right track. That's the idea. Interesting. Very good. Very good. Try and see what you can do about that. Solve. How would you do solve it? Your mind is in the right direction. So one person with it so far, and this is not, I'm not to, demean you, but to challenge you right now, the fact that I know this is tough, it's not easy, this kind of an idea. I can give a hint for those still working. Here's a hint for you, ready? In the numbers that we had a moment ago, like 54 and 45, right? Here's what I think of. 54 is really 5 10s and 4 1s. I should really just not put the S there. There are 5 of them, right, that are worth 10 and 4 that are worth 1. Whereas down here, what do you have? For 40. Yeah, 4 that are worth 10 and 5 that are worth 1. Try and use that as a little clue to help you. Okay, a little clue to help you. Very good. Now go about solve. Think about, if you're still confused, stuff like the cost of 2 items in a store. Pears are $2 a piece, apples are $3 a piece. It'd be like 2x plus 3y. Similar to this idea right here. So if you've got it, you're working, keep working. If you're struggling right now, take a look up and I'll go over what I'm talking about. So, here's what we know. Let me try and erase all this real quick. Hold on. All right. We know that initially the number is written like this. And then the number is written like this. Agreed? The units are just literally, the digits are literally just switching. And x is worth how much in the first scenario? In the first scenario, x spot is worth how much? 10. Hence the tens spot, right? So in this scenario, it's like 10x plus 1y. Okay? And now when we switch it, we get 10y plus 1x. Agreed? Just like we had a moment ago. And what do these have to differ by? More than?
36.
So you could just literally subtract the two and set it greater than 36. So you could say 10x plus y minus 10y plus x is greater than 36. Again, and it's difficult at first to see it, but if you go through the values, this unit spot is worth 1. This 10 spot is worth 10, plus the coefficients 10x and 1y. Here, the same thing happens, but reverse of it. Now, we know that when we subtract this minus this, we should get something bigger than 36. Well, this, on the upper left right here, okay, is really just this. So this minus this gives us a quantity greater than 36. Okay, greater than 36. Now, how would I go about solving? I just continue to solve this like any other expression. 10x minus x is really 9x. Y minus 10y is negative 9y, and that's greater than 36. Okay, so as a result, we divide through by 9. And we know that the difference between the quantities x and y, those digits themselves, have to be greater than 4. If that statement is true, you get answers that work. So for example, once we know that that statement is true right there, let's start with an XY table. For values of, let's say, x that are 1, what could y be such that the difference of them is greater than 4? Remember, these are odd numbers, by the way. The condition in the beginning was that they were odd, so there's limited possibilities. What could y be so that their difference is greater than 4? 5, okay. Well, 5 that would be equal to 4, right? 7 would be a possibility, and what else? 9. Now, when I noticed Nina was writing her notes, she wrote it like this, which is fine, because really it doesn't matter the order that we're subtracting them in, because we're switching the numbers anyway. So that's what she wrote. You could drop that absolute value because you know that you're switching them, or you could leave it to help. Think about this, ready? That means 17 and 71. That works, doesn't it? How about 19 and 91? That also works. So those are two possible answers we have so far. Again, for the number 1, these are the possible numbers. Numbers like 6 and 8 work also, but it said it was odd. So we could not use any even numbers in any of our choices. Again, it's an odd 2-digit number. So none of these can be even in this list. So although something like 16 and 61 would work, 18 and 81 would also work, we're not listing them now. Let's see. What about for the number, let's say 3 for this case? What would work for the number 3? What number that's also odd? 9, because 9 minus 3 is?
6.
Yeah, and 6 is greater than this 4 right here. Okay, it's greater than this 4 right here. Now, if we go back and look at the original statement that we started with, where are we? The original statement that we started with here, we knew that it was the y value that needed to be odd, right? This is where our starting point was. This needed to be odd to start. This could have been technically even or odd, but this needed to be odd. So there are other choices for x. I'm not even going to go into the other choices, but the idea is what I want you to see. You can take numbers and write expressions from them that relate in x and y. Okay, there's no review stuff. So you have some written exercises and then some word problems. It's a mix, okay? So please make sure you get to all this.